Hey guys, welcome to part 2 of the chapter 19 lecture. So we left off talking about different types of electrochemical cells. And the first type that we were talking about are these galvanic or voltaic cells. And these are ones that generate electricity. And we make them by taking a redox reaction, and instead of doing it in a single container, we separate the two half reactions into two different containers. So we put the oxidation reaction in one and the reduction reaction in the other, and we connect the two with a wire. And electrons can flow down that wire, and that electrical energy, the electricity, the energy that's made from those electron flows can do work, like light up a light bulb. So these half reactions, on the left here, we have the zinc losing electrons, and loss is oxidation. So this is the oxidation reaction. And this one here is the reduction reaction. Reduction is gain of electrons. And this, where the oxidation happens, we call this side the anode. And where the reduction happens, we call this the cathode. All right, the anode is negative and the cathode is positive, kind of like anions are negative and cations are positive. Okay, so in order for the galvanic cell to work, it's really important that you, A, have that wire there. So the electrodes must be connected by a wire. All right, because if they're not, then they're not connected, and you just have a piece of zinc in a container of zinc ions and a piece of copper in a container of copper ions doing nothing. It's when they're connected that this reaction occurs, that redox happens, that electrons flow always from the anode to the cathode. All right. And it doesn't really matter which, like if you put the anode on the left or the right. I'm not sure if there's actually a standard. I always put it on the left and the cathode on the right. I don't know, I'm right-handed. I like the electrons flowing right, and I like them in alphabetical order, anode then cathode. So the other thing that's important is that you have this thing here, the salt bridge. The two cells must be connected by a salt bridge, and this is to allow ions to flow between the two containers to balance charges, because on the oxidation side, the zinc is basically dissolving, the solid zinc is dissolving into solution and producing a buildup of zinc ions and of positive charge. And over on the other side, the copper is being deposited, so those copper ions are being removed from solution and being deposited on the solid, so you're losing positive charge. And so the positive charge can flow over here, and negative charge can flow over here to balance the charges so you don't get a charge buildup. If you do, then if you don't have the salt bridge, the reaction will go for a little bit, but then it'll ultimately stop, because what's happening is you would be building up, for example, in the anode, you'd be building up this zinc ion, and that would start to reverse this reaction. I suppose these are all reversible reactions. And Le Chatelier's principle would say that it would go in reverse, and so it would stop going forward. So the salt bridge helps to keep the reaction going forward by allowing those ions to flow. And we can take this cell that we've drawn here, this sort of like setup, and we can write it in shorthand notation, because, it's a lot of work to draw pictures of these setups. And so the shorthand notation for it is called the standard cell notation. And on the left side of this standard cell notation, we always write the anode components. So the anode electrode is the solid piece of metal that's sticking in the anode. And then followed by the anode electrolytes, so any ions in solution that are aqueous. All right, and we use a single line to divide the solid things from the aqueous things. We use a double bar to represent the salt bridge and separate the anode and cathode. And then we do the cathode electrolytes, and then a single line and the cathode electrode, which will be some kind of solid. So let's do a practice problem. All right, so we are given a redox reaction. It says write the half reactions and the standard cell notation for the following. So before we can write the half, so for the half reactions, we've got the oxidation reaction, which will happen at the anode. So I put anox and red cat. Those are my mnemonics for remembering that reduction happens at the cathode and oxidation happens at the anode. So we also need to write out our oxidation numbers so we can figure out which is getting oxidized and which is getting reduced. The solid aluminum and lead have an oxidation number of 0, and the ions have an oxidation number that matches their charge. So reduction is reduction of charge. So the aluminum goes from 0 to +3. That's gaining charge. The oxidation number is going up. So that's the aluminum. So I'll put aluminum here, which means that the lead must be getting reduced. It goes from a 2+ charge to a 0 charge. So let's do the aluminum half reaction. We have 2 aluminums here, so we've got to keep the stoichiometry. Oxidation is loss of electrons. So the electrons are on the product side. And we have 2 aluminum ions with a 3+ charge. So if each aluminum, to go from a 0 to a 3+ charge, it means it has to gain 3 electrons. And there's 2 of them. So a total of 6 electrons are gained. Now for the reduction reaction. In reduction, the thing that's being reduced is the charge or the oxidation number. So lead goes from, we've got 3 lead ions with a 2+ charge. Reduction is gain of electrons, so electrons will be on the reactant side. And the product is 3 lead atoms, solid. So each of those lead ions is gaining 2 electrons, and there's 3 of them, so 3 times 2 is 6. 6 electrons are gained. And we want to make sure that these electron numbers match, that they would cancel out, so that if we added these 2 reactions together, we would get this overall reaction here. And we do. So we've written out the half reactions, check. Now we need to write out the standard cell notation. So first we're going to do the anode side. So the anode is aluminum, the solid aluminum, that's the electrode. And then the aqueous components are the aluminum ions. Notice I don't need to include coefficients here. We're just writing out the species, no stoichiometry. Now I'm going to use a double line to represent the salt bridge and separate the anode and cathode. The cathode side is the reduction reaction. In aqueous solution, we have lead ions, and the electrode is solid lead. So that would be the standard cell notation for this galvanic cell or voltaic cell. All right, this one, the next problem asks us to sketch a voltaic cell for the following reaction. So in your Socrative online homework, there's not really a sketching tool for you to sketch these things. You might label one, but you should practice some problems where you actually have to sketch one. So I'm going to start by just sketching the components. So we need to have an anode and a cathode. Oops. We need to connect them with a salt bridge. Salt bridge. And we need to have some kind of electrode, solid piece in here. We need to have an aqueous solution in each one. And we need to connect them with a wire. And if this, we're going to call this one the anode, and this one the cathode. And no matter what these are made of, that means electrons will flow this way. They always flow from the anode to the cathode. So this would be like the rough sketch of any galvanic cell. And now what we're asked to do is basically determine which half reaction is going to go at each cell. So we've got nickel ion, which has a 2+ charge and an oxidation number of 2+. I'm assigning oxidation numbers for each of these species. And now I need to figure out which one is the anode and which is the cathode. So cathode, red cat, is the reduction reaction. which one's charge gets reduced? That would be the nickel, goes from 2 to 0. So over here, this is going to be the reduction reaction. Red cat. So that's the nickel, 2 plus, aqueous, gaining electrons to become nickel solid. And it's going to gain 2 electrons to go from 2 plus to 0 charge. So this electrode essentially is solid nickel. And in solution here, we have nickel ions, aqueous nickel. And the cathode is going to be the magnesium because its oxidation number goes up. Anode is oxidation. So we've got magnesium solid losing electrons to become magnesium ions. To go from a 0 to a 2 plus charge, you must lose 2 electrons. So that means that this electrode is made of magnesium, and in solution here we have magnesium ions. So we have just completely labeled this voltaic cell. Hooray! So, so far we've talked about galvanic cells where there's a solid and an aqueous form of the things that are getting reduced and oxidized. But sometimes both the oxidized and reduced form of an element are in the aqueous phase. They're in the same phase. And so you don't have a solid form of it to use as an electrode, but you by definition need to have an electrode, something for the electrons to travel from one place to another. And so in that case, we use inert metals or inert substances as an electrode. So common ones are platinum or graphite. And in your electrochemistry lab, we're going to be using graphite as electrodes. So here's an example problem. This is a redox reaction that takes place in an acid, hence the H plus there. All right. And we are going to show the two half reactions. So anox, red cat. All right, so I need to assign some oxidation numbers. 0 here, that's the only one that's a 0. H plus is clearly a +1. This ion is clearly a +2. Clearly a +2 oxidation number. Over here, water, hydrogen always has a +1 and oxygen always has a -2 as an oxidation number. And then over here, this oxygen always has a -2. So the only thing I've got to solve for is that manganese. Now, there's a total of -8 charge from those 4 oxygens, and I overall need to have a -1 charge. Okay, so if I have 4 oxygens at -2, that's a -8 charge. And I've got 1 manganese, all right, this is how I wanted to write this. I have 1 manganese at some charge X, and overall I need it to have a charge of -1 because of that charge there. And so what if X needs to be, so 1 times X needs to equal 7 because -8 plus 7 is -1. And so 1 times X equals 7, that means X is 7. So manganese is +7. This is another way to show that sort of algebraic breakdown in order to figure out that missing charge there. Okay, so I'm going to erase this mess and show the redox reaction. So the oxidation reaction is the one, or I like to start with the reduction reaction. So the reduction reaction is the one where the charge was reduced, where the charge went down. So let's see, iron went from 0 to a +2. That's going up. And manganese went from 7 to 2. That one's going down. That's the one that got reduced. So the manganese is reduced and the iron is oxidized. So I'm just going to put those as placeholders. And now we'll fill out those half reactions. So let's start with the iron. We have 5 irons, solid. Oxidation is loss, so electrons are lost. They're part of the products. And what happens is we end up with 5 iron ions with a 2+ charge. So they go from 0 to 2+, and there's 5 of them, so that's 10 electrons that were lost. Now for the manganese. The manganese is part of this polyatomic ion, this manganese oxide, okay? And there's 2 of these. And they are also reacting with those hydrogens and also, since they're getting reduced, they're gaining electrons. And then on the flip side, we end up with 2 manganese ions and some water, 8 H2Os that are liquid. The ions are always going to be aqueous in solution. So let's see, the manganese went from 7 to 2, so that means it gained 5 electrons, and there's 2 of them. 2 times 5 is 10. So that's good. These match. This one, the iron lost a total of 10 electrons, and the manganese gained a total of 10 electrons. So it's balanced. All right, now we can write out the sort of cell notation here for this. At the anode, we've got solid iron, so our anode electrode is solid iron. And what we have in the aqueous solution here is the iron ions, aqueous. And that's the anode, so now we'll separate with the salt bridge, and we'll write the parts of the cathode. So the cathode aqueous components are this manganese oxide, which is aqueous, the hydrogen, which is aqueous, and also the manganese ions are aqueous. So all of those we will list here. MnO4 minus, H plus, and Mn2 plus. And all of these should be labeled as aqueous. All right. What we don't have, though, is a solid. There's no solid listed at the cathode, but we still need an electrode there. So if there's no solid component, we add a solid electrode that's an inert gas like platinum or graphite. Okay, so that's how we do standard cell notation for different redox reactions. So we first have to identify the half reactions that are occurring at each cell, and then we can write it out in shorthand notation like so. So for these galvanic cells, these energy-producing electrochemical reactions, the energy that's produced by those electrons is different depending on how many electrons are transferred. And so we can sort of measure that energy that is produced. We call it the cell potential, or the electron motive force, EMF. And the units of EMF, or cell potential, are volts. Capital V is the abbreviation, which is why galvanic cells are also called voltaic cells. They generate volts of electricity. The maximum voltage that a cell can generate is called the E cell, or the energy of the cell, really. And at certain standard conditions of 25 degrees Celsius, 1 atmosphere, and 1 molar concentration of aqueous solutions, we say that's the standard cell potential. And we've seen that before in standard conditions are always represented with that little degree symbol. So we had standard enthalpies in previous chapters. We talked about standard heat of formation, the standard enthalpy of a reaction. All right, they all happen under standardized conditions. So that's what that little degree symbol means. So we can calculate the energy of the cell at standard conditions for different reactions. And we calculate them from these reduction potentials. So reduction potentials for a bunch of different redox reactions have already been conducted, and we can actually look them up on a table. And I will post this table for you. It's in your textbook on page 850 something. It's table 9.1, and it tells you all of the energy for reduction reactions under standard conditions. So it lists reduction half reactions and the energy produced by those reduction reactions. We can figure out the energy for the oxidation half reactions by simply reversing the sign. So we could say the energy of the oxidation reaction is equal to the negative energy of the reduction reaction. All right, so they're just opposite signs. So the energy of the cell, the E cell, the cell potential, all right, is equal to the energy or the potential, the oxidation potential, plus the reduction potential. Okay, and so we can look this one up on the table, and we can technically look this one up on the table, but we just have to reverse the sign. And we add those together and we get the cell potential. So let's do an example reaction so you can see what I'm talking about. What is the E cell, the cell potential, for this galvanic cell here? So remember, this is the anode, and that's where oxidation occurs. And this is the cathode, which is where reduction occurs. All right, and let's just write this equation up here as our reminder. E cell equals the oxidation potential plus the reduction potential. Okay, so if we go to that table 19.1, we can find that these two half reactions. All right, so the half reaction at the anode, sorry, the zinc is losing electrons. And at the cathode, the copper ions are gaining electrons. So we can look up these half reactions. So on the table 19.1, we can find the potential, all right, for this reduction reaction straight on that table is just positive 0.34 volts. All right, so that's the reduction reaction. For this one, for the oxidation reaction, we have to find this reverse reaction, the reduction reaction on the table, and it is negative. We'll see that it is negative 0.76 volts. All right, but we have to reverse that sign to make it an oxidation reaction, so it becomes positive. Okay, and now we just add these two together, and the standard cell potential here for this galvanic cell is 1.10 volts, positive. All right. For a galvanic cell, it will always be a positive value. In order for it to happen spontaneously, for electrons to flow spontaneously, then that number needs to be positive. If it's negative, then it's not actually a galvanic cell. The electrons are not going to flow spontaneously. All right, let's do another one. Calculate the standard cell potential for this reaction. All right, so for this one, we have to determine which is the anode and which is the cathode, which is the redox reaction and which is the oxidation reaction. Let's keep it consistent. I always do the oxidation reaction first, redox reaction second here. All right, so we've got oxidation numbers I'm just going to label here. So the lead is 2 plus and then it's 0. So the charge is going down, it's being reduced. So the lead is being reduced, which means the chromium is going to be oxidized. So we've got 3 lead 2 plus is reduction is gain of electrons to become 3 lead solid. And chromium is, we've got 2 chromiums and it's losing electrons to become 2 chromium ions. Okay, so, and it's losing let's see, it goes from 0 to 3, so each one's losing 3, and there's 2 of them, so that's 6 electrons. Oops, 6 electrons. And the lead is gaining 6 electrons. Okay, so those electrons will all cancel out, but now we need to look up the potential for each of these. So if we look at that table, it already lists the reduction potentials. So we're just looking for this reaction. Well, we find it, but we just find it for one lead ion. All right, so what we can find is the energy of reduction for 1. So this reaction here, though, is for 3. So we have to multiply that number. Nope, I lied. It doesn't matter. It doesn't matter. The stoichiometry doesn't matter. So whether it's 1 lead, 2 lead, 3 lead, 5 lead, it doesn't matter. The energy is still whatever it says on that table. So if we look it up on the table, lead 2+, and make sure that you're looking at the right charge. Sometimes ions can have multiple charges. So like we'll see that with chromium in a second. Okay, so the lead 2+, a little more than halfway down the table, has an energy, reduction energy of negative 0.13 volts as the units. And chromium, remember this is the chromium 3+ ion. So if we look down here, the reduction of chromium 3+, make sure it's 3+, being reduced to, so there's 2 values here. It says chromium 3+ being reduced to chromium 2+ ion, but what we have is chromium 3+ being reduced to chromium solid. So that's the one we want to use, and that has a reduction potential of negative, I just lost it, 0.73 volts. That's the reduction potential. All right, but we want the oxidation potential, so we have to reverse that sign. Okay, and now we just add the two together. 0.73 minus or plus negative 0.13 is positive 0.60 volts. That is our standard cell potential for this reaction. All right, which means that this will happen spontaneously. This will be truly a galvanic cell because it has a positive E cell. So the rules here is that a positive cell potential means that the reaction is spontaneous. All right, so any reduction, okay, and if it has a negative cell potential, it means that the reaction is non-spontaneous. So it won't go on its own. In other words, it won't form a galvanic cell. So you can eyeball just using that table 19.1, showing you the different reduction potentials, and you can figure it out. So I have this funny mnemonic here using that red cat and ox mnemonic. So any reduction reaction in table 19.1, if you pair it with the reverse of any reaction below it on the table, then it will be spontaneous. So think a red cat can sit on the back of an ox. That would work. An ox is big enough to carry a red cat. So if the reduction reaction is above the oxidation reaction in the table, it will be spontaneous, okay? But if the oxidation reaction is above the reduction reaction, it won't be spontaneous because an ox can't sit on a cat, is my sort of mnemonic there. You can't have an ox sitting on a cat. So any reduction reaction that's paired with the reverse, any reverse reaction that's above it on the table, okay, the cat can't be under the ox. So the reduction reaction cannot be lower than the oxidation reaction on the table. And that's like a quick way to determine whether the energy, whether the E cell is going to be positive and spontaneous or negative and non-spontaneous. So this is a good place to stop, and we'll pick up here, reminding us of these rules and being able to predict whether a reaction is going to be spontaneous or non-spontaneous.